here Professor Padmanabhan from IUCA in Pune, who is giving a Troisième Cycle course on advanced topics in general relativity. His assistant is Mark von Lanten, so if you have any questions, problems, he's here to help you.
Okay, thank you, Ruth. So before we start with the course itself, I want to get a few things sorted out. To begin with, how many of you are taking it for credit as a part of your course? Just put up your hand. No one. Okay, good. So that makes life very easy. Okay. Second, I want to explain a few things about the contact details, etc. You have already heard that Mark is my course assistant. There is a set of lecture notes of this course which is available. Okay. And it is available with Mark, and I think he is going to circulate a few copies here. And if you give him your email ID, I don't want it to be put on the web as a public domain thing yet. I have to work on it a bit more. So if you send him the email ID, he will be happy to send you a PDF file. This would save a lot of time for me in working through the algebra, because I can concentrate on concepts and more important things, and I can just say that you will find the algebra in the course notes. That is the format which I will follow. In addition to that, if any of you need to contact me at any time, the easiest thing is to send me an email, and this is the email ID, paddy at IUCA, IUCAA .yarnet.in. If you want to meet me or discuss anything in the course or any such stuff, just let me know by email. I'm not sure when you will catch me in the office. Ruth has told me that Thursdays I lecture and the rest of the days are mine. Okay, so, but you just send me an email and I will make myself available and we can discuss things. Then about the reference material for the course. There is no single textbook which will cover the material which I am going to talk to you in a single coherent unit. Okay. There is a book which I have written. It is titled Gravitation, Foundations and Frontiers. Gravitation, Foundations and Frontiers. This is going to be published by Cambridge University Press, and should we hit its hands around February, you can already place an order. There are 2 copies of it which is available with Mark, and he showed it to me today that it's 750 pages. So in case you feel up to it, you can take parts of it and look at it. Okay. The other standard reference which I would very strongly recommend you use is Landau and Lifshitz classical theory of fields, which is what I will be following most of the time. Except for the fact that I will be using a signature which is minus plus plus. So I'm going to use minus plus plus. Well, at least this is the declared intention, and if I don't use it, it's a mistake and we should correct the signs as and when it goes on. So this is different from the Landau-Lifshitz second edition convention, which is plus minus minus minus. So except for that, Landau and Lifshitz is a very good place to look up most of these topics. And I'm also going to concentrate throughout the course on conceptual issues and issues which are usually glozed on in the regular courses. So I will do the algebra, but algebra is just to supplement it. And the rest of the part of the thing you will find in the notes. So this is broadly what I wanted to do. I haven't missed any of the things which we discussed we should announce in the beginning. Yeah, that should be fine. So we will go for 1.5 hours, take a half an hour break, and then do for another 1.5 hours. That is the general structure. Now, what are the topics? The advanced topics was sort of a very nebulous kind of a title. What I plan to do is the following. In the first, that is the first Thursday and half of the next Thursday, I plan to discuss quantum field theory in curved spacetime. So I'm going to start with motivating what is known as a Rindler spacetime, and then discuss quite a bit of aspects of maximal extension of short scale metric and its connection with the Rindler metric. Then I will also try to introduce to you why you should expect something non-trivial to happen in these kinds of space-time by some classical argument, even before we do quantum field theory. Then I will try to give a rapid bird's eye view of the quantum field theory which I am going to need, because I am not sure how many of you know at what level of quantum field theory. So I will be using path integrals quite extensively, so I will just orient you towards that. And then I will do quantum field theory in curved spacetime and get the thermal effects in both Rindler prime as well as in black hole spacetime. This much should happen by middle of next lecture. Then the remaining part of next lecture as well as the third lecture, I will concentrate on action principle in general relativity and some several peculiar aspects of that, its comparison with spin 2 fields, etc. etc. That will be the second lecture. The third and the fourth lecture will discuss several aspects of extension of this action principle to what is known as Lamsau's Lovelock theories, essentially Lovelock theories, which has some very interesting thermodynamic properties as well, and something which I have loosely called a case study, that is electrostatics in a curved spacetime. This is done explicitly to show how even in some so-called elementary aspects of general relativity, there are things which you can work out and write papers about. This is going to be based on a paper which I have written just very recently, and there are fairly non-trivial amounts of material in that subject. So that's why I called it a case study. I don't know how much time I will have to cover that, but I will try to do that. Okay? So this is going to be the broadsheet. So let me start with the first topic, which is orienting you towards quantum field theory in curved spacetime. So with that motivation, we are going to start talking about coordinate systems for different observers. How you can operationally implement a coordinate system, and how non-trivial coordinate system for accelerated observers lead to very non-trivial kind of phenomena, which we can try to understand. So let us start at the very beginning, which is the concept of an event in special relativity. This is one of the terms where the physics meaning happens to be the same as the English meaning. An event is just what it is, an event. It requires for specification 4 numbers, when it occurred and where it occurred. Now the collection of all the events form the spacetime, and we know that the signature of the spacetime is this. And given that, you can form curves in the spacetime. In particular, we would be interested in the curves which denote the trajectories formed by material particles. So a curve I will denote by, let us say, xi of some parameter tau, which will be t of tau and x of tau. So tau is some parameter, and given for every value of tau I know the 4 numbers, so it gives me a parameterized curve in the spacetime. In principle, the curve is a geometrical object, while the tau is something which you choose. You can choose any tau you like. It is convenient for most purposes when we are talking about the curves, trajectories taken by material particles, to take tau to be the proper time as shown by the clock carried by the particle. Then we have the standard relation in special relativity, which tells you that the proper time tau, the proper time interval tau between two coordinate times, t1 and t2, is given by the expression integral dt square root of 1 minus v square of t. Or better still, if I take it as an indefinite integral to some time t, and put at t prime here, v square of t. Let us stare at it for a minute. So v square is the magnitude of the velocity square. V is just dx by dt, the standard, honest to God, classical mechanics 101 velocity. And c is set to unity. And this integral tells you what is the proper time. And you already know that the time interval integrated over this without this factor is multiplied by a factor less than unity. So as far as proper time concerned, when you move, you live longer, which is exactly what this equation tells you. When there is an elapse of 10 minutes here, there is only 8 minutes in the proper time clock. This particular expression has absolutely nothing to do with Lorentz transformations. I stress this because there are special relativity textbooks which unfortunately links it to Lorentz transformations. You take any particle, let it move along any trajectory, accelerated, rotating, zigzag, whatever, this formula holds. Accelerated motion is completely consistent with special relativity and can be discussed entirely within special relativity with no requirement of general relativity. Therefore, this is the first important piece to understand, and you can always do this. Now comes the concept of Lorentz transformation itself, and there are different ways of deriving Lorentz transformation. And it may appear a bit strange that in an advanced topics in general relativity I am going to derive Lorentz transformation, but that is being done with a particular purpose. Because I want to think of Lorentz transformation as just one among a general class of transformations. And we will need other class, and it is good to try it out in a specific context. What are we talking about? What we are talking about is the following. You have a space-time. So let me try to denote the space and time by, let us say, capital T and capital X. And I will try to be consistent. This is an inertial frame of reference. And there is a trajectory of a particle which is like this. Okay? So this is your xi of tau. We will do 1 plus 1 first. Now this observer wants to assign coordinates to this event. Okay? How does he do that? Now he can do it in any number of ways. As long as he has a unique marker for every event in space-time, he is done. The rest is only a translation table. But some way of doing it is nicer than some other ways, and I will try to explain to you a nice way of doing it. The nice way of doing this is he first sends a light signal from some point, and he is very clever and he has originally arranged mirrors and gadgets all over the place. So he sends a light signal from here. Let us say that this is the trajectory parameterized by the proper time tau. So at a time, let us say tau 1, he sends a light signal and he gets the light signal reflected back. And he gets it at the time tau 2. So he can measure tau 1 and tau 2 and he knows it was reflected from this event. Using that information, he wants to assign coordinates to this event. Now the most natural set of coordinates he can assign happens to be the following. He can assign the coordinates of this, I will use lowercase letters, t and x. So he is going to give for t the coordinate half of tau 2 minus tau 1, and he is going to give the coordinate x to be half of tau 2 minus tau. Why does it make sense? Well, the way he will reason it out is the following. My light beam was in transit for a time interval tau 2 minus tau 1, and it was all the time traveling with a velocity unity. So in tau 2 minus tau 1, it would have traveled a distance 2x, and half of that is the distance to that point. This makes eminent sense if I am not moving, so I will use the same definition. Similarly, it was reflected at some point and came back, and I will take the symmetric midpoint as the time of event at which it is reflected. Because after all, you want to choose something which makes sense when you are not moving, and this one makes sense when you are not moving. Now using that, and given this trajectory, you can immediately write down the transformation laws between t, x and capital T and capital X. Okay? So that is because this is in this line and this is in this line, and you just have to solve for those equations. So that is done in the notes, so I won't go through that. Essentially, it is convenient to use at this stage the, it's not really necessary, but it is convenient to use u, which is t minus x, v, which is t plus x. So instead of assigning t and x, if I assign u and v, I am through. And there is corresponding capital U, which is capital T minus x, and capital V, which is capital T plus x. So we want a transformation between these set. What is given to you is this trajectory, and I will say that the trajectory is given by the functions. Let me just say trajectory that is given by two functions, which I will call, let us say, f naught of tau and f1 of tau. It's a parameterized curve, and F0 gives you corresponding to the time coordinates, and F1 gives you the space coordinate. Okay? So you are given this trajectory, and then you want to find what is the relationship between capital U and capital V related to small v and small v. That relationship happens to be the following.
Are you students coming from Lausanne?
Yes, we are.
So, is this not convenient for you to start?
There are works in the highway, so we're a bit late. And also parking
okay,
was
so you came by car. Okay, it's not that
next
it's
week
late.
we will.
Okay. Okay, so that's an exception.
Okay, fine. So we don't have to change anything. Right, yeah.
Sorry, as we interrupted you, can you break the chalk, please?
Break the chalk because it's squeezed.
Yeah.
Okay. That is a nice song. Let me see whether there is a broken chalk. There are broken chalks. Yeah. All right. So the relationship between these coordinate system, I will just try to write it down. Okay, it is most conveniently written, as I said, in terms of U and V. So this is capital U, which is like t minus x, will turn out to be F0 of small u minus F1 of small u, and capital V will turn out to be F0 of small v plus F1 of small v. I just want to make sure I got my signs, everything right. That's correct. Now there are quite a lot of things here which you need to understand. The first point is that in one-dimensional motion, if a person is traveling along any arbitrary trajectory determined by this, and he is assigning coordinates using this. This is originally due to Hermann-Bonte, and these are called the radar coordinates. And if you use this method to assign coordinates, then u gets mapped to a function of u, and v gets mapped to a function of u. Okay? It doesn't mix t and x. So using t and x is not such a good idea because this is much nicer, and this is what it does. And there is a fairly complicated way of generalizing it into three-dimensional motion. What you essentially do is that you send a light beam and you get it back. But you have to arrange the mirrors are carefully angled in such a way that you will get it back, correcting for aberration, etc. Then you use two angular coordinates using the photon trajectory, and then you do the radial coordinate by the same method. But we won't need that, so I'm not going to go into that. Just believe me that it can be done. The second point is, okay, I came up with some crazy way of doing this. What happens if this guy was moving with uniform velocity? What kind of transformation does it give? So let us try it out. So in the case of uniform velocity, what we will have is we first have to decide on the two trajectories. So the F0 of tau is the time as a function of the proper time. So if you look here, the time as a function of proper time will be gamma times tau. So it is gamma tau. Gamma is 1 over root 1 minus v square. Then the F1 of tau is just v times t. So it is, okay, I'll write it as beta gamma tau. Beta is the velocity of the observer. I was about to write v, but I have found that I have using both lowercase v and uppercase v for something else. So in order to distinguish between that, beta is the velocity with which you are moving. Gamma is 1 over root 1 minus beta square. So you have these trajectories, and let us plug it into that. So if you plug it into that, you will get capital U equals F0 of small u. So F0 is this quantity, that is gamma u minus gamma beta u, which is u gamma into 1 minus beta. Gamma is 1 over root 1 minus beta square. So this gives you u into square root of 1 minus beta upon 1 plus beta. Okay? Yeah.
C equals 1.
I am always going to work with C equals 1. C is 1. And you look at the V, which you can work out in a similar fashion, and the only thing will change is the sign of this, and you will find that this is equal to V in the square root of 1 plus beta upon 1 minus beta. So if the observer is moving with uniform velocity and he sets up this coordinate system, you will find that he is just contracting along the u line because of this 1 minus beta and is elongating along the v line, keeping uv equals constant. This is the right way to look at Lorentz transformation, believe me. People use x and t and it's a mess. Okay? So all that you are doing is that you take one coordinate, contract by a factor f, and you take the other coordinate, elongate it by a factor f. Okay? That is what Lorentz transformation does. So you also know immediately that if I write down the line integral ds square, incidentally at any time if I am going too fast, let me know and I will slow down. If I am too slow, that also it is worth commenting on, but that you wait for one more lecture. Okay? Because these are elementary stuff. So ds square, which is minus dt square plus dx square, is just minus du dv. But here just u and v are multiplied by some product, so there is no d's on that. So absolutely trivially this goes into minus du dv. So if you use this light cones and this kind of a coordinate system, it turns out that ds square is invariant. No big deal, we know that. Okay? But it gives you the operational significance behind Lorentz transformation. Let me try to stress that. See, you have been taught that there is this coordinate system x and t, and then there is an x prime t prime, which is gamma into x minus vt and gamma into t plus vx, etc. etc. But these are just transformation. How do you know that the guy who is moving with uniform velocity is actually going to use these coordinate systems? Okay? Now that justification is given here. Because the entire Lorentz transformation of special relativity is built out of speed of light remaining invariant, from that you can obtain the light cones being, the ds square being invariant. From that you can obtain this. This is the way, for example, Landau and Lifshitz will obtain in classical theory of field. They will derive this before Lorentz transformation. And that is the way it should be done. Once you have got that, you have a nice way of parameterizing curves. Once you have parameterization of the curves, there is a way of setting up the coordinate system using constancy of speed of light. And this you can do for any trajectory you like. And then as a result, you get Lorentz transformation, which is this particular case. Now, the bonus is that I am now no longer tied to Lorentz transformation. You give me any trajectory, f0 and f1, I will tell you what is going to happen. Okay? And that is what we are going to do next. We are now going to talk about a uniformly accelerated observer. And we want to work out the coordinates used by that observer and what happens to ds square in that front. So everything up to this point is a warm-up for that. Okay. So let us talk about a uniformly accelerated observer. So for a uniformly accelerated observer, I first find out the trajectory. So I only have a definition that he is a uniformly accelerated observer. So let us start from that definition. So in special relativity, a uniformly accelerated observer will follow your equation like v over root 1 minus v square equals some constant which I will call kappa. Okay? So I want to know what trajectory this is. Very easy. You integrate, you get kappa t on the right hand side, assuming v is equal to 0 or t is equal to 0. Solve for v, which you equate as dx by dt, and then you integrate on second. If you do all that, fairly straightforward, you will find that the trajectory is given by x square minus t square equals 1 over kappa square. Okay. Now, of course, you have chosen a choice for the origin of x and t. You can shift x by x naught and t by t naught, but that doesn't make any change. Another note on notation, here of course you will have c square dt square. What about this kappa square? The quantity c square over acceleration, that is c square over g, any acceleration, has the dimensions of length. And if you ever need to make sort of numerical estimate, remember that if it is Earth's acceleration, c square over g happens to be 1 light year. So that is typically the length scale we are talking about. So since, and c square is 1, so 1 by g has dimensions of length, so 1 by g square has the correct dimension. This is what you will find. Now once you know the velocity, you can also integrate that equation, tau equals integral dt root 1 minus v square, and find the relationship between the proper time and the coordinate. And once you know that, you can plug it in and reparameterize this in terms of the proper time itself. If you do that, you will find that the same trajectory can be described as capital X equals 1 upon kappa cos h of kappa tau, and capital T is equal to 1 upon kappa sin h of kappa tau. So what kind of curve is this? This is a hyperbola. So what we are talking about here in this case is a particle which is moving in this xt plane. This is x, this is t. Let me draw these 45-degree lines here. These are the light cones through the origin. And the curve x square minus t square is 1 upon kappa square is this hyperbola, which asymptotes to this x is equal to plus or minus t lines. And when t is equal to 0, this distance is 1 upon kappa, but that is because of our choice of origin. You can shift it around. And this is a hyperbola which you have. Okay? Now already you can find a few interesting things about this. Suppose you do have a uniformly accelerated observer in this space-time who is following this trajectory. The first thing you realize without any deep thinking is that he or she is never going to get any signals from this part of the space-time. If you take any point here and you send signals, it can only go like this, it can't cross this line. So this line x is equal to plus t acts as a horizon for this observer. He is not going to get anything out of that. Remember all these because it turns out that while a uniformly accelerated observer, somebody who is eternally uniformly accelerated in flat space-time, is a bit of a myth, because after all he is going to start with the speed of light and end with the speed of light. But everything I am going to say is going to hold true for, let us say, short sail metric or any other metric where these observers are genuine, honest to God, R is equal to constant. So it is well worth spending time trying to understand this. That is why I am going to spend time on this part before we get into black hole physics and stuff like that. So there is a horizon here, and from this part of it you will not get any signals. And similarly, he will never be able to send signals to this part of the space-time. Right? So by and large, if you take regions which are both causally connected to him and the regions to which he can causally connect, that is going to be just this quadrant. And the curve is entirely on that quadrant. In particular, if I write down just this equation and ask you to find the trajectory, this is not the complete answer, because this equation is obviously symmetric under x going to minus x and t going to minus t. So I could have drawn another hyperbola here. So there are pairs of hyperbola. But that is not the case with this equation. That is a good thing about parameterizing the curves rather than writing it as functional relations. So when you take this part, then you know that for every tau I have to give you a point, And as your time coordinate goes from minus infinity to plus infinity, first of all, tau is equal to 0 is mapped to t is equal to 0. So the t is equal to 0 is the sort of line of symmetry. Okay? And then tau is equal to minus infinity is where the particle is starting from, and tau is equal to plus infinity is where it is ending. That is the way the trajectory goes. So the clock is going to read minus infinity here and plus infinity here, and this is how the curve will go. Everything which we have done here is completely cautious, so to speak. We just assume that a particle is moving with uniform acceleration, integrated it, and what is this? I emphasize because pretty quickly we will end up getting bizarre situations using this particular case. So it is good to remember that we haven't done anything illegal so far. Fine. So this is the trajectory. And now I want to know what kind of coordinate system this observer is going to give. So we go back to our trick by which we can set up the coordinate systems. And we know that f0 is this. This is my function f0 of tau, because that gives the time. And this is the function f1 of tau, which gives the spatial part. And then I just have to repeat the exercise which we have done here between capital U and small u. So let us try to do that. So capital U equals f0 of small u minus f1 of small u. So f0 of small u will have 1 upon kappa sin h of kappa u minus you will have cos h of kappa u from f1. So this is going to be the sin h minus cos h, so it has a negative sign, overall negative sign, minus 1 upon kappa e to the minus kappa u. Please keep an eye open for algebraic errors, because if I make an algebraic mistake, we'll have to go back, waste a lot of time correcting it. So if I miss a sign or something, just put up your hand and let me know. And capital V, by the same token, will be 1 upon kappa. The sign is flipped to plus and everything else is the same, so you are adding the two of them. So the negative part will go away and you will end up getting e to the kappa. This is again well worth remembering. The mapping, when we went from inertial frame to a uniformly moving frame, was a linear mapping between u and v to small u and small u. Here is an exponential map, and the reverse map will be logarithmic, and that logarithm has a lot to do with black hole physics. Okay, that is, small u or small v will be related to capital U or capital V by a logarithm. So given this, we can now again calculate du and dv. So this tells me that capital Du is going to be, the minus signs go away, e to the minus kappa u du, and similarly dv is e to the kappa v dv. Okay? So how does the line interval look like? If I look at ds square, which is minus du dv in my inertial frame, that is going to now look like minus just the product of these two. So that is going to be e to the kappa v minus u du dv, which is minus goes with this one, minus e to the v minus u, v has a t plus x, and this has a t minus x, so t goes away, and you have a positive sign there, 2 kappa x du dv. So I can now write this as minus dt square plus dx square. And just to make the whole thing complete, I will write du dv also as this. So that is going to be minus dt square plus dx square. This is our first non-trivial result of the day. Let us now pause and see what it means. What we did was, we started with a method for assigning coordinates to the event. Then we considered two different observers. One observer was moving with a uniform velocity, and we used that method. And we found that we are led to a linear transformation between u and v, and the metric ds square remained invariant. Du dv went to du dv. Then we said, okay, we have done uniformly moving guy, and now let us take a uniform acceleration. So you took a uniformly accelerated observer, we found the trajectory, parameterized it exactly the way we did before, and then went through the exercise. This time we found that capital U and capital V are related to small u and small v by an exponential mapping. So dv du is not an invariant, but you can calculate what it is. So the original metric, the flat spacetime metric, will appear to be this for an accelerated observer, okay, who is using these coordinates. This is fine because it is just a non-initial coordinate transformation, so we do expect metrics to change. Now this is known as a Rindler metric. This or various avatars of that is called Rindler metric. So I want to derive a few more of forms which will be useful, and then we will get on with the physics of it. So you have got this, and you may also want to write down the transformation equations which we have written down here. The u and v are given in terms of this, but for most practical purposes it is convenient to have the transformation in x and y as well. Okay, so that can be written down in very many different ways. So one way I will do after doing a little bit more transformations on that, and that we did. Okay, what is the transformation I want to do? This is the expression for ds square. So let us first change this part into, I want to take e to the kx dx square together and define a new coordinate system. Let us say dx bar, which is e to the kappa x dx. Okay, so that this whole thing I can call as dx bar square. So if I do that, this implies x bar is 1 over kappa e to the kappa x. Therefore, this metric can also be written as, I have e to the kappa x dt square. Now, e to the kappa x is nothing but kappa x bar. So I can write it as kappa square x bar square dt square with a minus sign plus dx bar square. So the Rindler metric can also be written in this form. And this form has a very intriguing interpretation, so I want to spend some time looking at that. You see, all along we have been using the standard metric of the special relativity, with a time having the interval in the time having a minus sign. Now, very often it is convenient in quantum field theory and in various situations to go into what is known as analytic continuation to imaginary samples. So what I would like to do in these cases is that you can think of, let us say, IT as some variable which I will call TE, E for Euclidean. Okay? So instead of real time, I am putting an I on that and I am calling this Euclidean. This is a completely illegal transformation as a coordinate transformation, but as an analytic continuation I can think about this and study what functions look like in that. So if you do that, my metric now becomes ds square in the Euclidean space as plus dt square plus dx square. Okay? Now look at what happens to this when I do exactly the same in the Rindler time. So just as I do this, I will also take the Rindler time IT and call it T Euclidean. Then this matrix becomes equal to kappa square x bar square dte square plus dx square, dx bar square. Now this metric must be familiar to everyone. If I take this kappa and take Te and call kappa Te as some theta, this is dr square plus r square d theta square. This is just flat two-dimensional sheet of paper in polar coordinates. Of course, this is flat two-dimensional sheet of paper in Cartesian coordinate. So this transformation, the entire transformation is just going as simple as from going from the Cartesian coordinates to polar coordinates in a plain sheet of paper. Okay. It also tells you that in order for that transformation to work nicely, and I will define what nicely is if time permits later on in GR, that you want this kappa times Te, which is like the angle theta, to be periodic with a period 2 pi. This means this imaginary time coordinate physically should exhibit a periodicity of 2 pi over kappa. Okay, and it will turn out to be crucial. And anyone who knows condensed matter physics will already smell a temperature out of this, and that is how the temperature comes out. Now there are one more thing which is relevant at this stage. This transformation I can also do on this. What happens then? Then under this transformation, you find that you have kappa x, capital X, going over to cosine of kappa tau e, because I am also making the same transformation I times tau as tau e. All time coordinates are changed into imaginary values. And similarly, kappa times Te here is equal to sine kappa times tau. This was a hyperbola, this is a circle, right? So this trajectory which I drew as a hyperbola in the real space-time, if I do the same thing in x Te plane, this curve and this 1 over kappa will become a circle. Originally it was like this. Just to give you an idea. Okay? So while this guy is merely going from minus infinity to plus infinity along this fellow is just going round and round in a circle. And the periodicity is manifest. And so is the coordinate transformations which are. Okay? So all this is why I said that even though you start with things which look eminently reasonable, things get out of hand pretty quickly. Okay? And if you go the analytic continuation, this is what happens. Now, the transformation rules between this x bar and original coordinate system, you could have worked out from this. But now that I have shown you this relation, it's very obvious what it is going to be. Okay? So the transformation rules there will be, if you take kappa times x, or even, I don't even need kappa times x, x will be equal to x bar cos x kappa tau, and t will be equal to x bar sin h kappa tau. This is the Rindler coordinate transformation. I want to stress, yeah.
Silly question, does he Do you actually go round and round in that circle, or do you go exactly once round?
No, you go round and round in that circle. I'll tell you what. You take this and take the value kappa ta equals 2 pi. Okay? Then you take a value kappa ta equals, let's say, 2 pi plus 0.5. In the original hyperbola, when I put kappa ta is equal to 2 pi, you will be at some point. It will be somewhere here. Right? And when I increase kappa ta beyond that 2 pi, I go a bit further. Right? When you make the analytic continuation, that is like cosine of theta being equal to 2 pi and a value greater than 2 pi. So by the time you have gone from some point here to some point here, you have already gone around the circle once. And next time when you go a bit further, you go around again. It's very bizarre. Okay? And in fact, if you want to realize that all this is complete nonsense and one should not believe in any of this, the following is the proof. You think of a guy who was at rest up to this point and then goes off like this. So there is a perfectly smooth curve like that. Now you try to map it here. That would work. You can draw a straight line here up to this point. That straight line will map to this straight line. Then he is going off like this, which you can make round and round in circles. If he doesn't do anything else, you are fine. Now suppose at some stage he decides to stop accelerating and take off with uniform velocity. And you try to map it here. You will find that you cannot do it continuously. Because the point where he is taking off is a physical point somewhere here. And the curve doesn't even get there. Okay? So you have to keep these things in mind. So you have to use it up to a point where the results are reasonable and can be cross-checked by another method. But it is fun. I mean, there is something very interesting which is going on here. That's why I wanted to introduce it right up front. Okay.
And what happens
Yeah.
to the horizon?
There is no horizon. And in fact, I am going to describe that in much greater detail. I am going to describe what is going to happen to all the 4 regions when I do the coordinate transformation. You will find that the region inside the horizon gets into this point. The whole thing shrinks into a point. And so I'll come back to that. Okay, so first, one more comment at this stage. This might look very similar to these equations we wrote on here. But they are physically very, very different. What this equation tells you is the trajectory of a given observer with some choices made for initial conditions. What this equation tells you is a coordinate transformation between capital X, capital T to small t and x bar. Okay? This is a global coordinate transformation mapping every point with every other point, most of them in fact. Okay? So, in particular, in this coordinate transformation, if I take x bar equals constant, some particular value of a constant, that will correspond to a uniformly accelerated trajectory. So, if I take x bar is equal to the people who are sitting ideally at a given value of the spatial coordinates in this metric are uniformly accelerating with respect to the inertial frame. That is what this metric or this metric tells you. Fine.
Sorry.
Yeah.
For that coordinate transformation, should not be there the t, the small t, instead of
Oh yes, absolutely. Thank you so much. This is a mistake. It is small t. Yeah, that's correct. Because I was just writing down the coordinate transformation from this and the other one. Yeah, I just made a mistake. It is t. So it is a coordinate transformation while this is a trajectory with tau as the product. So what it tells you, just to repeat once again, that if I take an observer at a constant x bar, he is going to be uniformly accelerated and the time shown by his clock when he is at kappa x is equal to 1 will be this, which is correct. Right? So when x bar is equal to 1 by kappa, this will become 1 by kappa. And this metric will tell you that the t becomes his tau because it is a proper time when I put dx is equal to 0 and kappa x is equal to u. Okay. So that is what is happening. Fine. Now I want to go further. So we started around 2:15. So we'll go on till 3:45 and then break. Will that be fine? And then 3:15 we will come back again. And we will, 4:15 we will come back again and we will do another 1.5 hours. Okay. So let us look at this metric with a slightly greater detail. So I need to rub out these and right here. Alright. So we again start with the metric which we have written down just now, which is minus kappa square x bar square dt square plus dx bar square, and these are obtained from your original metric by capital X equals x bar cos h of kappa t and t equals x bar sin h of kappa t. Okay. Now I want to introduce a slightly different coordinate description on this. In order to do that, I am going to call kappa square x bar square, which is appearing here, as let us say 2 kappa L. This defines for me the new spatial coordinate L. So that tells you that L is just half kappa x bar square. So dl is kappa x bar dx bar. So I have to write x bar in terms of these quantities. So kappa x bar, I'll put kappa L here. So I have a kappa square x bar square. So kappa x bar is going to be square root of 2 kappa L. Dx bar. So I plug that into this metric, then I get ds square equals minus, this is designed to give you 2 kappa L here, dt square plus this dx bar square, that is going to be dl square divided by 2 kappa L. Now that comes just from this. Now I forgot to tell you that there are 2 transverse coordinates we live in 4 dimension unless you are a string theorist. So the y and z, they are going for a ride in all this. Y prime is y and z prime is z, etc. So I can add to it dy square plus dz square everywhere, but I am not doing that. Okay, imagine that that is that. So this is the, or if you want to be explicit, I will just write d some capital L transverse square. This dimension don't play any role in what we are discussing. So we have again mapped the same description into another coordinate system. So by now you will be getting pretty tired of how many more coordinate transformations we are going to do, but this is just about the last one which we need, and there is a good reason for this coordinate system. This coordinate system has the form that what is going on here as g naught naught, it is a reciprocal which is going to appear in 1 upon GR. And it turns out that a host of metrics, spherically symmetric metrics, which we are going to be interested in, including short scale metric, has exactly this form. So now I am going to do the next step of connecting in this Rindler frame with something more realistic, like short scale metric or a de Sitter metric or a Resner-Nostra metric, etc. and ask about the Rindler approximation to such metrics and what happens in that case. Okay, that is what we are going to do next. So there is also one more thing which is worth remembering here. When I did this transformation, I can go back and substitute for this x, somewhere I would have written it down. Yeah, here. This kappa x bar is square root of 2 kappa L. So I can write these expressions with square root of 2 kappa L, so I get immediately the coordinate transformation. But there is something peculiar which is happening here. Once I have this metric, I can actually think of L as either positive or negative. Okay, which I could not have done with any reasonable effectiveness here. Here if I take positive x or negative x, it is going to be just x bar square. While here if I take positive L and negative L, the signature actually flips. Okay? So the coordinate transformations are not as innocent as they appear to be in most of the general relativity, especially in situations like this. So keep that in mind, we will come back to it. Now why am I doing this? The reason I am doing this is because there is a host of metrics, as I told you, in general relativity, which has the form minus some f of r dt square plus dr square by f of r. This is the sort of standard notation we want to use, plus some dl transverse square. This could be a spherically symmetric r square d theta square plus n square theta difference. Now I am assuming, since this is a sort of advanced course and everyone has done the first course, that you know metrics of this form. For example, if f of r is equal to, say, 1 minus 2m by r, which sometimes for convenience I will also use the notation 1 minus rg by r, where rg is just 2m. This will give you the short scale metric. And you can have Resnel Nostrum by just adding q square by r square and d theta by adding a h square r square. You must have been all taught that Einstein's equations are horribly nonlinear. Okay? And then they will go on and teach you how to do spherically symmetric cases. It turns out that metrics for like this, if you write down Einstein's equation, it is a linear equation. It's a linear differential equation in F, as a result of which superposition works. That is why you can start with short cell, then you can add a charge q square by r square, then you can add a cosmological constant, it will be h square r square. The idea works. If we have time, we will get back to it at some time. But it turns out that is a linear differential equation in this particular case. So we are looking at metrics of this kind, and we want to just extract the essence out of it. The essence is actually happening here r is equal to 2m, where there is a horizon. At least we have been told there is a horizon, and we want to look at it more carefully. So what I will do is to look at a general metric of this kind, and then I will ask what is happening to this metric at a particular point, where I will assume that f at some rh, which is h for horizon, is 0, it vanishes, but f prime at rh is non-zero. So it is a simple 0 there, so f prime at rh is not 0, and that quantity I will just call twice kappa. Okay. Why am I calling it kappa? It's going to look like the kappa which I have used in the Rendler frame very soon. Okay, so I don't want to use another notation and bring it back. So this is the notation. This is just a constant which is fixed by the metric, and you can compute it for any such metric. If this is the case, then I can write down f of r near the horizon as f at rh, that is 0, plus f prime at rh, which is 2 kappa, into r minus rh. This is near the horizon, and this r minus rh I will call L. So this becomes 2 kappa L. Okay. So this metric reduces to this metric. The near horizon limit of this metric is the same as this. With the 2 kappas identified. So the kappa here was the acceleration of an observer. So it is some kind of an acceleration. And here also this kappa happens to be what is known as the surface gravity, which is essentially the acceleration. If you work this out for the short scale metric, it will turn out to be exactly the Newtonian acceleration, which is gm by r square, evaluated at r is equal to 2m. It will match perfectly. And there is a more sophisticated way of convincing yourself why this is some kind of an acceleration. But these two things will match. So what we have done is that if you are given a metric of this kind with this property, near the horizon, I can map it to a Rendler. Of course, Rendler metric we know is flat because it can be transformed to the inertial metric, while this metric is not flat. That is just because at that local path you have a local inertial frame, and that local inertial frame doesn't appear in the inertial coordinates but in Rindler coordinates when you do this expansion. That is the only thing to know. Okay? Fine. Now what can we do with that? I mean, there is a lot of good uses it can be put to, so I am going to do one or two of them. First of all, let us look at the coordinate transformations between this metric and the flash metric a little bit more carefully. Because, yeah.
Sorry, this observation is valid only if there's 1, 0 for the function.
Actually, it turns out, that's a good question. Actually, it turns out that the way I'm going to do it, it will be valid near every 0 of that function with a different k. So suppose I have several isolated symbol poles, like it will happen in the short sail de-Sitter case. Suppose I have 1 minus 2m by r plus h square r square. Then I have two horizons. Near each of the horizons I can define a different kappa and do this approximation near that. And it turns out it works. Okay, so it can be done, but most of the time I will be concentrating on just one horizon, which will turn out to be bad enough. Okay, so this is the connection between these two, and now I want to examine this a little bit more closely. So the first thing we notice is that we had these coordinate systems, which I just said that this capital X can be written as square root of 2 kappa L cos h of kappa T, and capital T is square root of 2 kappa L sin h of kappa T. This also immediately tells you that if I do x square minus t square, I get just 2 kappa L. Right? And I can take the ratio and get kappa t as well, which is the inverse transformation. Now we know from this relationship that since cos h is always greater than sin h, as far as the magnitude goes, your x is greater than t. So this particular coordinate transformation which I have written down is valid only in one quarter of the space now. This is t, this is x, and I had this 45-degree lines. And the transformations with L greater than 0 are valid only in this quadrant.
So naively, I would have expected if L goes negative, I would go inside the horizon.
That's correct. That is what I am going to do.
Anyway.
I am going to do how you can go inside the horizon. That is precisely the point. I could not have done it here, and then I just did a coordinate transformation and I said, oh, come on, be a friend, I am just making a coordinate transformation. You will find that it is a lot more than a coordinate transformation. Okay? So let us look at it more carefully. So let us look at this, as I said, purely as transformations between xt and L and t, small t, capital X and capital T, and L and small t, and let us examine it. First of all, let us assume small l is greater than 0. Then these lines, these curves, are going to be hyperbola. So I can draw those hyperbola. These are for some L is equal to constant. Constant greater than 0. Okay? Now suppose I take L negative, then I will get hyperbolas here. This is L is equal to constant but less than 0. That is easy. That just flips t square to t square minus 6. So I have hyperbolas here and hyperbolas here, and it goes very continuously. L is equal to 0 corresponds to x is equal to plus or minus t. X is equal to plus t is this line, and this line is L is equal to minus t. So this is L is equal to 0, which is your horizon.
But then t must also be imaginary.
Yeah, I'm going to come to t. Now let us see what small t does. When you do t, you find that it has to make two copies. First of all, when small t goes from minus infinity to plus infinity. Okay, so let us first look at constant t levels. Okay, so if I take the ratio between these two, I get the second inverse transformation, which is tan h of kappa t, which is sin h upon cos h, is equal to t divided by capital X. So constant t lines are straight lines through the origin with some slope. So let me draw those lines. This line is t is equal to constant. T is equal to 0 line is this. Take this one, okay. T is equal to 0 line is this. Positive t lines are here. Negative t lines are here. And this line actually corresponds to t is equal to minus infinity. And this line corresponds to t is equal to plus infinity. So the t, as it goes from minus infinity to plus infinity, you cover this entire region. And then you again start at t is equal to plus infinity, and you go all the way here. There are lines of constant t here. And that covers this. This is completely bizarre. So we have to understand what is going on here. What is going on here is what is known as maximal analytic extension of a manifold. Okay? And this is the simplest example you can think of. That is why I started with this, because it looks completely innocent and understandable, but it has all the features. Suppose for a minute that I didn't do any Rindler-Frein uniformly accelerated trajectory, nothing. I just gave you this metric. If I just give you this metric and say study it, what would you do? First you will calculate its Riemann-Christoffel tensor and you will find it is flat. Then you may be able to find a transformation which will explicitly use it as a flat. You can do all that. But you will also notice that in this particular coordinate system, L is equal to 0 is funny. One of them blows up and the other one goes to 0. Then you will remember, that happened at short scale metric too. And then maybe there is some way of getting out of that. Now, if I can go back to the other coordinate system, of course I have got out of it. But I would also like to know what happens when I do that. What happens is the following. If you take 2 points, x, t, and minus x minus t, this equation left hand side doesn't know about the sign flip. If you simultaneously flip, this also doesn't know. So 2 points, x, t, and minus x minus t, gets mapped to the same L and small t under this coordinate transformation. So in some sense it is an illegal coordinate transformation, but it turns out that physically most of the time we'll have to deal with coordinates like L and t. The short scale coordinates are like that. So every point here, if I take this point here and you take a corresponding point here, they are different in capital X, capital T coordinates, but they are the same in small l and small t coordinates. So if I had this coordinate metric given to me, unless I investigate this, I will end up thinking that L going from minus infinity to plus infinity, T going to minus infinity to plus infinity is my whole world, which it is not. It is only half of my whole world, because it only covers these two regions, and there is an analytic extension which takes care of these two regions. Okay? So this is what is happening. Now, you can do other things. For example, in this regime, what is the kind of coordinate transformation I want to write down? So these coordinate transformations which I have written down is valid in, okay, let me draw one more because it has become very cluttered. This is called the right verge, this region. This is called the left verge, and people usually call this F and P, like future and past, I mean the future and past of the origin. So in the right and left verge, these coordinate transformations are found. Okay? On the top and the bottom, obviously you can't use this, but you just have to flip the sin h and cos h. Because the t becomes x and the x becomes t. And then you will get these hyperbolas nicely parameterized. Okay? So once you have done that, I mean, most of these details are in the notes, that is why I am not doing the algebra at every stage, but let us concentrate on the concept. And the coordinate L, most importantly, goes from a positive value here, nicely through 0 here, and to negative values here. Okay. Now let us go back to those metrics. Suppose you are given short scale, and you are given short scale metric, and you have an f of r, and you know that near the horizon this is the transformation, and if you go from r greater than 2m to r less than 2m, what you are doing is just what you said. Your L is going from positive values to negative values, And in some analytically continued manifold, R greater than 2m will sit here. In the case of a short scale metric, the R greater than 2m will sit here, R less than 2m will sit here. Of course, R also happens to be bounded from 0, which is not a problem for x coordinate, but that is irrelevant. And this line will be R is equal to 2.
Can I comment?
Yeah.
I think that in all this business of analytical continuation, you are using the fact that you have geodesics of proper length, which is finite, which end.
Right. Actually, I didn't even mention geodesics so far.
Yeah, but otherwise you could also say, okay, can I extend my manifold at x going to infinity?
What going to infinity?
Can I make this kind of maximal continuation when x goes to infinity?
X going to infinity. Yes, you can.
Well,
yeah, as a mathematical maximum.
But
yeah.
The point is that to go there you need an infinite time.
Yeah.
That's the point.
No, it does. But as far as I said, this is remarkably devoid of physics so far.
Perfect.
Okay, so I can make this maximal analytic extension, and I will find that my manifold structure has doubled, which is what I am stressing right now. And then you should ask if there is an observer, what can he do and what he cannot do. And that will be causal restrictions on what he can do. Perfectly correct. Okay, but we haven't even got to that yet. Okay, so this is R is, but that's a good question because we may never get to that. Okay, so this is R greater than 2m, and this is R is equal to 2m, and this is R less than 2m. And the coordinate system which is usually given to you, the short scale coordinate system, covers this region and this region, which is this metric. You know, the R goes from 0 to infinity, and that covers this region. But if you make an analytic continuation, analytic extension, you will find that there are 2 more regions which are coming in. And that comes as a great shock if you don't short scale metric the usual way. So that is why you should start with this metric, which looks completely innocent. And here you have L, and then you make a coordinate transformation to flat space-time. And you will find that this L and T coordinates cover only this part and this part. And when you do the analytic extension, you find these 2 events. There you don't show any surprise because we are so accustomed to thinking of flat space-time in inertial coordinates as sacred. And the Riddler metric is some creature which somebody has brought in. Okay? While in the short scale metric, the situation is exactly opposite. People think of this R and T as very nice coordinates, and then it becomes as a shock that it doesn't cover the whole manifold. So that is why I wanted to do it in this inverted way. Okay. Now let us go further and put it to some use. What we are going to do is to use this information, what we have, in order to find nice set of coordinates for metrics of this kind. Okay? So what do I mean by nice set of coordinates? If I look at this, this particular metric with this coordinate system, I see some pathologies. I see that this thing is vanishing and this thing is blowing up. So I want to avoid that. And now I am not going to make an assumption that it is flat space-time. It is not. It is some curved space-time. And how do I go about doing it? I will try to do this step by step just to see how this can be done, even if you have not read any textbook. It is fairly obvious from there. We have to again make more coordinate transformations. So you take ds square and you first pull out this f of r. So you get f of r. Then I write it as minus dt square plus, I will call this dr star square, where I have defined my first new coordinates as r star, which is integral over dr of f of r. Okay, so I just pulled it out and have redefined this. Now this, I don't know the form of f of r because it's a general metric, except that I know near the horizon, so near r is equal to rh, f of r has this form which is 2 kappa l. So if I integrate that, I will get there 2 kappa in the denominator, and it's a logarithm, so it is log, and again it is nice to normalize it by choosing the constant so that the same 2 kappa appears here. Let us do that. So near horizon, it has this form. So near horizon, I know that 2 kappa L goes as exponential 2 kappa R star. This is near the horizon. Therefore, this metric is going to, this metric has f of r, and remember that f of r is 2 kappa L near the horizon. So near the horizon, it is going to pick up a e to the 2 kappa r star. That is still no good, because all that I have done is that L is equal to 0 was the singularity, and by just doing that dl over L, I have just shot off the singularity to minus infinity. That doesn't really help. So it is still singular. I want to avoid that singularity. So I will do the next step. I'll just say that let me introduce the u and v coordinates now. So this is f of, it has to be written in terms of u and v, minus some du dv, where u and v are defined by the usual relation, u is equal to t minus r star now, and v is called t plus r star. Now for those of you who have seen this before, the r star is what is known as the tortoise coordinate, essentially because it is logarithmic and it goes very slowly near r is equal to 2m. And the r star going from minus infinity to plus infinity covers the region outside the horizon. So you get this, and you have this du dv defined through that. And then you examine this, what happens near the horizon. Again, near the horizon, f of r, which is 2 kappa L, is going to have e to the 2 kappa r star. Now r star is obtained by subtracting v minus u, that will be 2 v minus u dv du with a minus sign. So we know that this is how it is going to behave near the horizon. That suggests the way. What you do now is you define two new coordinates by doing these integrals. You define a new v as integral e to the kappa v dv. That takes care of this. And you define a new u as integral e to the minus kappa u dv. So just to recapitulate, given any f of r, you define an r star by this integral. Then you define a new u and v by these expression relations, and then transform to a capital V and capital U by this. Then you go into again a new capital R and capital T by taking this u plus v combination. You are assured now that near what was originally a singularity, this spacetime is actually going to look like an approximately flat metric. That is because this e to the kappa v dv is going to become dv, and this e to the minus kappa u du is going to become d capital U. So this metric can be changed into minus du dv near the horizon. Okay? This might look like black magic, but it is legitimate operations. So I have given you a form by which any metric of this form can be made non-singular. I can define for you a new set of coordinates in which this metric will be non-singular in the new coordinate system. So let me write down that final expression. Just want to make sure I'm getting the signs right again. Yeah. Kappa x is equal to e to the kappa r star cos h of t, and similarly kappa t is equal to e to the kappa r star sin h of kappa t, where originally you had a metric which was ds square equals minus f dt square plus dr square by f, and the only new coordinate we have introduced is this r star, which is equal to integral dr over f of r. So if anybody gives you a metric of this form and you define this r star like this and use r star and t to define two new coordinates, capital S and capital T, and write down the final metric in terms of x and t, that metric is assured to be non-singular everywhere. So you can do this for short scale metric, for example. In the case of short scale metric, your r star will be integral over dr is 1 minus 2m is, let me call it rg by r. So this is integral r over r minus rg dr. So write it as r minus rg plus rg, so it is r plus rg log, and again by choosing a suitable constant, modulus of r by rg minus 1. Okay, so there is an explicit transformation between r star and this, and you can also compute kappa for this. You just have to do a Taylor expansion on that, and you will find that I also told you that kappa happens to be just m divided by 2m the whole square. It's the acceleration, Newtonian acceleration at the short scale radius, which is 1 upon 4m, which is just 1 by 2 rg. Okay. So if you now go ahead and substitute these expressions into this, you can write down what the coordinate transformation. Yeah.
Have you removed a singularity by doing a singular transformation of coordinates?
Okay. It is not a singular transformation, but since the question has come up, let me try to give a more complete answer. Let us consider another metric in which I can probably make this better answer. Think of the metric which is just an aside, but let us just clarify this. D theta square plus sine square theta. This may not screech, but writing with this is very difficult. So there's an optimum length, let us try. Sine square theta, close your ears. That's all right, d phi square. Now I'm going to use this quantity as some mu. Okay? In that case, this metric, I think, will become d mu square upon 1 minus mu square plus mu square d phi square. I'm quoting from memory, but we can check the algebra. Okay? Because 1 minus mu square will be, okay, this is mu square. This is cos square theta. D mu, when you do a sine theta, there will be a cos theta and d theta. Cos square theta will cancel out d theta. Now let us stare at these two metrics in order to answer your question. This metric is clearly pathological at mu is equal to plus or minus 1. So it looks as though there is a singularity at mu is equal to plus or minus 1. If I hadn't given you this metric, just given you this metric, you will say that yeah, mu is equal to plus or minus 1 looks funny. Then I make a coordinate transformation which is mu is equal to sine theta, which is not singular, and I get it into this form. This is precisely what is happening there. And we know that this manifold is not singular everywhere. It's just the surface of the sphere. Okay? So this is a coordinate singularity. So whenever you are working with coordinate singularity, there is this problem. And the question is, I mean, you can go into some aspects of measure theory on this space of functions in order to understand what you mean by a singular transformation. It's not as simple as one would think of. So mu is equal to sine theta if you think it's a singular transform in some definition. Then of course this is a singular transform and everything which we are doing uses the singular transform. But in the conventional terminology in differential manifold, you wouldn't think of the zeros of a function getting back to each other as a singular transformation. And when you divide by the quotients, the zeros can come and sit in the denominator. That is what is happening. So coordinate singularities are completely eliminatable by coordinate transformations, which are not singular, but it requires what I would call elimination of zeros, okay? Which is exactly what is happening here. Okay, so let me go further to this, and we are almost there. So how do these expressions look like? I don't want to even rewrite it, but just look at this exponential kappa r star, what it looks like for short cycle. If you look at exponential kappa r star, the kappa r star will be kappa r here, so that will be some e to the kappa r, so that is e to the r by 2 rg. Then you have another kappa rg, that is half, and there is a logarithm. So you get r over rg minus 1 to the power half. Okay. So you take this expression, multiply by cos h of kt and multiply by sin h of kt, define your two new variables, and then if you do that, the metric you get is the following. ds square, which was originally minus 1 minus rg by r dt square plus dr square upon 1 minus rg by r. This was the original singular metric. That will become equal to 4 rg square by r rg square by r e to the minus r by rg minus dt square plus dx square. This is known as the Kruskal coordinates. So what we have done is that this particular metric with r and t had an apparent bad behavior at r is equal to rg. I went through these coordinate transformations, which I have written down here. And when you do that, the same metric appears like this. Here, there is no singularity at r is equal to rg. If you take r is equal to rg, it is 1 by e or some such thing. Okay? So there is nothing funny which is happening. So this is the proof of the pudding is in eating. So you have an explicit coordinate transformation which gives you Schwarzschild metric in a non-singular form. This is just like going from that 1 d mu square upon 1 minus mu square going into d theta square plus sine square theta d. Yes?
Is it correct to say that you do a coordinate transformation in the region where it's well defined?
Is it correct to say that I do it in a region which is well...
Let's take the metric top left.
Right.
So the second form. So there you can do a coordinate transformation as long as mu is not equal to 1. I mean, wherever it's defined, you can transform.
Yeah, the point is we want to do it where mu is equal to 1.
No, but I would say, I'm asking, is it correct to say we do it as well where mu is not equal to 1? And then the new form, we can continue it?
Yeah, no, I understand what you mean. It is, you are asking, is it like defining gamma function for a negative argument by defining gamma function for positive and analytically continuing? What I am saying is that you don't need it because the mu is equal to sine theta transformation. If I just write down an equation, mu equals sine theta, there is absolutely no restriction on this transformation.
Right.
And theta is equal to pi by 2, mu is equal to 1. Or theta is equal to minus pi by 2, it is minus 1. Right?
Mu larger than 1 easily.
Yeah, that is right. That means the mu is bounded between minus 1 and plus 1. But that is okay. You can have a coordinate, after all, whenever you use angular coordinates, we know that it is bounded between 0 and 2 pi. No one ever said that all coordinates should have infinite range. When you use polar coordinates, r goes only from 0 to infinity, x goes from minus infinity to plus infinity. That is not an issue. But there is nowhere does this equation exhibit bad behavior. So that was the point, because it's important, so let us thrash it out. The question he raised was that, look, you had a metric which was singular at some point. Maybe you cheated by giving a singular coordinate transformation which just cancelled that singularity. Okay? I'm saying yes, you are almost there. What I did was not to remove a singularity, but I removed a zero. There's a slight difference between these two in the mathematical sense. Of course, the reciprocal of a zero will be a singularity in the sense of infinity. Okay? But what is going on here is that this coordinate transformation, as I said, all these things about what is a singular transformation and what is allowed transformations required some concept of measure theory on the space of functions, which I am not going to go into. But this coordinate transformation, virtually everyone will accept is a good, nice coordinate transformation, which is nowhere similar. At the same time, if I look at this metric, the metric is blowing up at mu is equal to plus or minus 1. And if I use this coordinate transformation, I can remove it. What is happening if you really want to understand it in terms of analytic continuation? It is the difference between integrable singularities and non-integrable singularities, which happens in integration. If I had a dx upon 1 over root x, I can integrate it across x is equal to 0, because it becomes root x, even though the integrand is not well defined at that point. That is precisely what is happening here. This is d mu upon square root upon minus mu square, near the point where we are worried about. And that quantity is being transformed into d theta. Okay? So, I would claim this is an allowed transformation. Yeah. So now let us get back to this. So this coordinate transformations, when you carry it out, this is what you get. However, here is where our old problem surfaces again. These coordinate transformations I have written down is only valid when since cos h is greater than this, it is only valid on capital X, modulus of x being greater than modulus of t. Therefore, this entire procedure covers only one quarter of the spacetime. Okay? The other quarter comes to you free of charge, because you can just go in this L from positive to negative, but in the process you double up the spacetime. So I'd like to again draw that picture, which I will do here. I probably need this, but anyway, we will come back to that. So in the short-scale metric, what happens is the following. So I have a coordinate system. This is my capital T, capital X coordinate system. Okay? And then I have these lines, 45-degree lines. The transformations which I have written down works in this quadrant. And you first find that if I draw R is equal to constant lines, which is same as R star equals constant. So if I keep this as constant, then x square minus t square is some constant, that is the hyperbola. Okay? And this will correspond, R is equal to constant greater than 2m. That is what you will get. This will correspond to R is equal to 2m. And R less than 2m will be hyperbolas here. This is r less than 2. Here you cannot use these transformations because this only covers the other quadrant, but you just flip this sign 90%. Okay, and if you do that, you get the coordinate transformations which cover this region. Okay. So you have covered these two, and what about t? The t coordinates are straight lines through the origin again, because if you take the ratio, it is x by t which is being fixed, and this is some t equals constant greater than 0. So this is t is equal to minus infinity, and this is t is equal to plus infinity. It actually makes sense because all of you must have studied short scale metric at some level. So if I have a particle which is falling in, the particle is following, if you are using clocks which are defined outside the horizon, the t clocks in that metric, the standard short scale metric, the particle when it crosses this point, it would have clocked infinite time in the coordinates. But it would have clocked finite time in the proper time, which we have not even brought in yet. And it will just cross smoothly through that, from r greater than 2m to r less than 2m, but the t goes to this. And then t makes one more circuit around this. The only new complication in the short scale spacetime, which is not there, I mean all these is deja vu, because this is Rendler to inertia. The only new complication is that there is a r is equal to 0 surface you can write down, which is a genuine physical singularity. You find that things are blowing up at r is equal to 0, which is not there in Rendler. So things stop here, and we don't know what is happening there, so we won't even talk about it. So, but until you reach that, this region, the coordinate transformations are fun. But all this is life above this line on the right. What is going on here? This region is r less than 2m, this region is r greater than 2m, and I have written it in a coordinate system in which there is a nice non-singular behavior on this line, on the horizon. But in the process, I discovered that there are two more regions. And these two regions you would not have discovered originally because the coordinate transformations are multiple valued in x square minus t square and x by t. So any point which I take here and its mirror image here, they both get mapped in the short scale metric to the same point. Now when I describe the whole thing in Rendler frame, you would have told yourself, yeah, I understand that, but inertial frame is a nice frame. That is what I should be using, and Rendler frame is because some guy was accelerating to eternity, and that is why I run into all these trouble. But what happens now? Now, your intuition would tell you that short scale metric is a nice metric. This r is equal to constant is where I am sitting. If sun is described by a short scale metric, we are at r equals theta equals phi equals constant line. Maybe our clocks are maybe these clocks are taking the time which is measured by this dt. Okay, so this is perfectly understandable. Except that it is wrong. The good coordinate system for short scale are the crystal coordinates. Can I get a glass of water? Oh, it's not easy. Yeah, maybe we could. Yeah, maybe we could stop. Yeah, we should be stopping. We'll come back and do this. Yeah, right, perfect. Do I have to take questions now, or we will discuss after this session? Okay, fine. So we will do it after they come back. Yeah. So where we left off was to discuss this transformation, which essentially takes this metric and puts it into this form. And we were having some discussion over the coffee again about the singular transformations and non-singular transformations, etc. The way to think about this is that if this factor was not there, this is just flat space-time. And in the flat space-time, I gave you a set of transformations, somewhat like this, which took it into the Rendler coordinate system, which had the form some g naught naught dt square plus 1 upon that same factor dr square, right? And that form had a problem at L is equal to 0. L less than 0 and L greater than 0 were separated by a horizon for that accelerated observer, and we did this whole thing. Similarly, I could have started by using these coordinates and solving Einstein's equations. In fact, if you read Chandrasekhar's book on the mathematical theory of black holes, he will never introduce this spherically symmetric line element for short side metric. Because he will start with this, he will write down Einstein's equations in this metric, solve them, and show that this is the solution. And then he will say that if you restrict yourself to a particular region in that, then you can introduce another set of coordinate systems which are spherically symmetric, in which the metric looks like this. Then he will come and say, well, of course, the transformation which goes from here to here, he is introducing a singularity at some point. So it's a bad transformation at that point. So it's very crystal clear that your manifold is perfectly fine, there is no singularity at R is equal to RG, and it is a transformation which is going to do this. The reason we are interested in it is that this transformation has a lot of similarities with this Rindler coordinate transformation. And the Rindler coordinate transformation, I told you that when you go into analytically extend to imaginary time, etc., shows some periodicities in the imaginary time. And the trajectory, which is a hyperbola, gets mapped into a circle. All these things happen even here. Those have nothing to do with these things about whether it is mathematical issues like whether it's a singular transformation or not. Because if you look at these transformations, again I can go from T to TE, cosine and sin h will become cosine and sine. Nothing happens to this. And this will just pick up the corresponding imaginary time. And the R star equals constant, which is like R is equal to constant curves, which are hyperbolas here, are going to go into full circles. Now the question is, what is going to happen to this region and this region? This is what Ruth was asking some time back. These regions just disappear. Okay. When you do this transformation, the right way to again think about this is that the curve x square minus t square equals constant is a hyperbola. That becomes x square plus t square equals constant, which is a circle. And that circle has a radius. Now when you keep decreasing the radius of that circle, this is like in the Rindler frame, remember the length scale is inversely related to the acceleration by c square by g. When you go to larger and larger accelerations, the hyperbola starts straddling this horizon closer and closer. When the acceleration is infinite, they degenerate into these two lines. But these two long infinite lines becomes a point in the Euclidean space. So it is essentially the transformation that x square minus t square, let me call this some length L square, which is 1 over kappa square. This goes to x square plus te square, the Euclidean time square, equals L square in the Euclidean space. Now if I keep letting this L go into smaller and smaller values, and finally let it go to 0, x square minus t square equals 0 are two straight lines. X square plus t square equals 0 is a point. X equals 0, t equals 0. So the entire horizon gets submerged to a point, and the region which is inside the horizon just vanishes. In some sense, the Euclidean TD is nicer TD because if you are an observer outside the horizon and you don't care what is going on inside the horizon, your entire manifold is covered by the Euclidean set. In some other sense, it is a bad set of coordinates to use because it completely misses the physics on R less than 2. So that is the first point. The second point is that when you write a metric like this, I am using this coordinate R, but of course my coordinates now are t and x, which means I have to invert these transformations and express R in terms of capital T and capital X, which of course you can do. I mean, just mathematics is oriental, but you can write it down. There is a transformation which will tell you that. But what it is telling you is that the metric now depends on capital T. So the Schwarzschild metric is a time-dependent metric. It is not static. Don't believe it is static. It looks static in the spherical coordinates at r greater than 2m. At r less than 2m, it is again not static. Because at r less than 2m, the time coordinate is actually r, not t, because the signature flips. So the timeline coordinate is the one which has a dr square from there, because that has the correct sign. And the metric does depend on small r. So even in the Schwarzschild metric, for r less than 2m, it is wrong to say that the metric is static. And that is very clear in this kind of a notation, because this metric coefficient is explicitly time dependent. You can can work it out. You can work out what the time dependence is. So that is another peculiar feature which we completely miss when we do the short scale metric in the spherical polar coordinate. So now we are not talking about coordinate transformation, we are talking about physics, whether something depends on time or not. And you cannot use the standard RT coordinates because of this bad behavior and the sign flip at r is equal to 2, which is avoided here, and you can explicitly see that the metric is time dependent. So if you see effects which are usually seen in time dependent metrics, you don't have to be surprised. That is the second point. And the third, yeah.
Sorry. There's another thing about the two metrics, Schwarzschild and Kruskal. When the Schwarzschild radius goes to 0,
right.
In one case it's smooth, and the other one something happens.
Yes, it's something happens. And in fact, we will come back to it when we define the temperature of the short scale metric, because while the entropy vanishes for flat space, then the temperature blows up to infinity. That is obvious here, because you have this RG which is non-analytic dependence RG. So when m goes to 0, you don't recover the flat space time. It is true, and nobody knows the way out of that. And it is also true, but I have sort of briefly mentioned it, that the xt coordinates in principle is extendable all the way to infinity. But there is a physical barrier at r is equal to 0, beyond which you don't know how to extend because there is a physical singularity there. And because everything gets multiplied by factor 2, there is also a physical singularity here. The diametrically opposite points have the same behavior there. Usually you get away from all these by saying that in any physical context when you want to study black holes, you have some collapsing structure, and that collapsing structure will have some trajectory which would have started from somewhere and it would have fallen in, and the region on this side is short scale metric is anyway not valid, and you would have removed it. So that is something which you can do, but if you just take the short scale metric as a one parameter family of Einstein solutions parameterized by m, then you do run into these problems which you have to keep in mind. Okay, so I have covered most of what I wanted to say about these analytic extensions, and I just want you to keep this physical picture in mind, that there is a tx coordinates and a small t small r or small t small x coordinates, and these are the same in Rendler as well as in Schwarzschild or in de Sitter or in Resner-Nostrum, in the host of metrics with f of r with a simple 0 at r is equal to a near that this is the structure which you have. And the observers who are here will perceive this as a horizon. Now what changes is the physical interpretation you attribute to these observers. In the flat space time, these are uniformly accelerated observers. So you would say that no, they are not physical, and the guys who are vertically going like this are physical. In the short scale metric, the same person will claim that these are very physical observers, because these are like the observers who is staying away at some fixed distance from, let us say, the sun. While an observer who is going like this, I don't even know what the Kruskal time and Kruskal space coordinates is, so they don't look physical. I mean, this is just something which we have to get used to, and there is nothing which mathematics can tell you. And the full analytic extension of the manifold in both the cases is in Tx coordinate system, which is like the inertial frame is like Kruskal, short scale frame is like Rendler. Now this is closely related to the fact that if you ask any man in the street, drop a stone and ask whether it is falling down, he will say it is accelerating. If you put a stone on the table, he will say it is not accelerating. A general relativist will answer exactly the opposite. He will say that a freely falling stone is not accelerating, a stone which is kept on the table is accelerating like anybody's business. So that is the way general relativity views things. In the same way, an observer who is at r is equal to constant is accelerating, and that is why he gets mapped to a Rendler observer. Fine. Now I want to give you the first glimpse of where things like temperature etc. emerges in this space-time. For that, I am going to follow exactly the same route we followed between Lorentz transformations and accelerated frame transformations. I am going to ask, suppose I have a space-time and there is some wave phenomena going on in this space-time. I will define it more precisely in a moment. And I have an observer who is viewing this wave. What will he see? Okay. So just to make it concrete, let us think in terms of scalar waves or scalar fields, and let us consider trajectories in this space-time. So we are doing flat space-time again. This is x, this is t, And let us assume there is a wave field all over the place. Okay? I'm going to assume that there is some scalar field which goes as, let us say, e to the minus I omega t minus x. Okay? Some plane wave with a frequency omega greater than 0 moving along the positive x-axis. Okay? Now if I have an observer with some trajectory, and he goes around measuring what is this field phi at every point. So he measures when he is here, when he is here, when he is there, etc. as a function of his proper time tau. So what was here a function of, let us say, t and x. So you start with a scalar function phi of t comma x, and you map it along the trajectory of the observer. So that becomes a phi of the proper time tau of the observer, which I can write down by, this is the definition of phi at t of tau, comma x of tau. Okay, for any given trajectory I can do that. So he is saying the phi to vary with time along some line, and you may want to ask, what does he attribute? What kind of frequency does he attribute to this? So let us again try to do that. So in the case of Lorentz transformation, suppose the observer is moving along a uniform velocity trajectory, then we know that his x is equal to some gamma v tau, and t is equal to gamma tau. We have done this. So your x minus t, which is just the u coordinate, which we did it just a little while ago, is going to be tau gamma into and if we do t minus x, that is easy, t minus x 1 minus capital V, which we know is tau square root of 1 minus v by 1 plus v. Okay? So your phi of tau, this is uniform velocity v, observer, is going to see this e to the minus I omega tau as exponential minus I omega t minus x, which is going to be tau into root of 1 minus v over 1 plus v. Absolutely no surprise, but as I said, this is just a warm-up. So you have a plain monochromatic wave in one front. The observer who is moving through with uniform velocity will again see it as a plain monochromatic wave, but he will attribute to it a different frequency, which is capital omega times this, which is just your Doppler shift. No surprise. Okay. Now let us do it for a uniformly accelerated observer. So for a uniformly accelerated observer, capital X we know is 1 over kappa cos h of kappa tau, and capital T is 1 over kappa sin h of kappa tau. So your t minus x becomes 1 over kappa sin h minus cos h. So that is again with a minus sign, e to the minus kappa tau. So that tells you that the same e to the minus I omega t minus x, this is the wave which we have. Under uniform velocity, this is what it became, and under uniform acceleration, you are going to get now exponential minus I omega, that minus sign takes care of this into kappa, e to the minus kappa tau. This is a bizarre result, but I can write it in a slightly different form, which will probably make it more palatable. Suppose I write it as exponential minus I some integral some omega of tau deta. Okay, so this omega of tau is derivative of this with an extra minus sign. So then you will find that omega of tau is just capital omega e to the minus kappa tau. What it tells you is that if I have a plane wave in some space-time and I have a uniformly accelerating observer going through that wave and measuring it with respect to the watch he is wearing, he will say that the plane wave is undergoing exponential redshift. The frequency omega, which he will attribute, is time dependent, and it comes from the original frequency multiplied by an e to the minus kappa tau. As time goes on, it is going to be redshift. So this is the way any sensible electrical engineer would have defined the instantaneous frequency of a wave. The phase is defined as an integral, or the derivative of the phase is defined as the instantaneous frequency. So it's a time-dependent frequency problem in the physics sense of the word. But then it is no longer monochromatic. So the next question which you can ask is, if it is not monochromatic, what is its power spectrum? So you define the power spectrum of these waves by saying you have the phi of tau, and I can take e to the, let us see, minus I nu tau d tau integral. This will define me the Fourier transform, which let me call this f of nu. And the power spectrum will be mod f nu square. Okay? And you can go and compute that. So it is interesting because you have to do this integral here, and the phi of tau is exponential of an exponential. Because the phi of tau is going to be this quantity. So it is exponential of an exponentially decreasing thing, and you have to do its Fourier transform. This is doable, some fairly elementary complex analytic integration, so I will not go through the details of that, but I will just write down the final result. This turns out to be very interesting. What you get is the following. You will find that f of nu is given by a little bit complicated expression, so I will just write it down. 1 over kappa omega over kappa I nu over kappa gamma function of minus I nu by kappa exponential of I nu by 2. There is absolutely no physical meaning to it or thought can be attributed to this. Some horrendous expression. Except that when you calculate the power spectrum from that, power per logarithmic interval, so it is nicer to think in terms of mod f of nu whole square. And in particular, I will look at the negative frequencies. This, when you compute, you find that this is given by beta divided by e to the beta nu minus 1, where beta is kappa think is a remarkable result. What it tells you is that the power spectrum of the wave is Planckian, and it has a temperature beta, and beta is related to kappa over 2 pi, which is where kappa is the acceleration of the observer. So if I have a plane wave in some spectrum and I run through it with a detector, I am going to interpret the Fourier power spectrum of that wave to be made of a Planckian noise with a temperature which is proportional to the acceleration which we can do. Now there are several points which need to be stressed on this, so let us go through one by one. The transformation f of nu dependent on capital omega, which was the original frequency of the wave. But when you take mod square, that goes away, as you can easily see. Okay. So whatever is the original wave, when you do this Fourier transform, you are going to get the Planck spectrum in this nu. Now the second point has to do with this negative frequencies. Why am I emphasizing the negative frequencies? This classically has no real meaning. Of course, most of the electrical engineers again would have just flipped it to make it into positive frequency. But quantum mechanically it means something. Suppose for a minute, instead of scalar wave, think of it as some real electromagnetic wave. And suppose it is coupled to a system which you are accelerating with. Now your system has two energy levels. And then we know from the time-dependent perturbation theory that if I have a perturbation which is varying as e to the I omega t or e to the minus I omega t, it will either induce upward transitions or downward transitions. So the negative frequency waves are going to cause one kind of transition, and the positive frequency waves will cause another kind of transition. And the interesting thing about the Planckian spectrum is that f at nu divided by f at minus nu is just e to the beta minus beta nu, which is the Boltzmann factor. So if the two levels are going to be populated by exactly the inverse relation, then the transitions caused in the upward direction and transitions caused in the downward direction will remain the same, as a result of which you will say that the upward and downward are populated by the ratio e to the minus beta. This is exactly the same as saying that whatever gadget I am having which is coupled to this is kept inside a box with some thermal radiation. Because when it equilibrates, this is what is going to happen. Okay. So in that sense, that is why I put this factor in, but that was only for this picture. The other thing has to do with the role of H cross, the Planck's constant. There is no H cross in this picture. There is a purely classical result. Just to make sure that there is nothing which has gone missing in the c equals 1, etc., I told you that kappa has dimensions of acceleration. So I told you that c square over g has the dimensions of length. Right? What I have is a factor g times nu. So if I take g times nu, I put a nu here, you can easily see that this quantity doesn't require any H cross factors. Because g over c square has dimensions of length inverse, or rather g by c square has dimensions of 1 over length. So if I want to get a frequency dimension, I only have to multiply it by c. This has dimensions of frequency. Okay, so that is precisely what is happening here. Beta is the beta inverse is the temperature. Yeah. Temperature is kappa over 2 pi. So beta has exactly the same dimension, and beta nu is without any H cross, purely with c factors, will give you exactly the right dimension. So how is it that there is anything? Yeah.
So in the classical case, though, you need the field to be there. If you have no field, you have
no. We'll come back to that. Yes, but this expression I could have written as e to the beta nu as b to the nu over nu naught, where nu naught is a purely classical frequency. If you are a radio astronomer and you are measuring this intensity field, you will not require any photon picture, and you will just take the wave picture and you will say that this is a purely classical result. The reason quantum mechanics comes in is that I could have multiplied this by h and divided by h, and then I could have thought of h nu as an energy, and then this h is going into the denominator, which means that the temperature will pick up a h proportionality or a h cross proportionality. So the temperature in that case, when you are writing it in terms of energy, will be proportional to H cross, and that temperature can be thought of as a quantum effect. But at this level, there is no quantum effect involved. It is a purely classical effect. I haven't even done quantum theory. The only place where I have brought in a little bit of quantum ideas is at very starting point where I wrote down a phi and said it is like e to the minus I omega t minus x. So this is like a wave which is existing in real space-time, but a complex wave. Okay. Now, usually nobody bats an eyelid when I write a wave as e to the minus I omega t minus x, because there is an understanding that you will take real part in the end. But you can't go around getting power spectra, which are squares of things, and then say that I will take the real part. So this is actually a complex wave which I am working with. Now, it's a very interesting exercise for anyone to do. What happens if you work with, let us say, cosine of omega minus omega into t minus x, and do the same exercise? The answer is extremely interesting. The corresponding thing for this will become n plus half plus square root of n into n plus 1 cosine of some theta, where n is given by this. Okay, except this beta factor, I 1 over that quantity. And this is remarkable because n is like a Planckian spectrum of number of particles at a given mode, mean number of bosons in a thermal spectrum. Half is n plus half is your standard half in the harmonic oscillator, half x cross omega. Root of n into n plus 1 is the fluctuations around the mean in a thermal distribution. And this theta is related to the phase between the cosine wave's phase and the 0 point of the oscillator, 0 point of the accelerated agent. So you can get this result. I am not going to discuss it in this course. I will give a reference in the notes. So it tells you that even if you use a real wave, you do get part of it. But in the complex wave, it is a lot simpler and you get just a plain Planckian. So coming back to your question, I need a classical wave in order to get this result. In quantum mechanics, or in quantum field theory, the 0 point fluctuations of the field very naturally provides me with this wave. And in that sense, it's a purely quantum mechanical result. But if I have a real wave, I mean, real versus complex, not real, but real in the sense of the English real. If I have a real wave, then I can do this Fourier transform and get this result. So what is the key idea? The key idea is hidden in this particular mathematics of Fourier transforming exponentially redshifting spectrum. A Fourier transform of an exponentially redshifting spectrum has a form like this, whose mode square is Planckian. Okay, it comes from this gamma square and this when you do this property. So whenever you see an exponentially redshifted spectrum, you can almost guess that there is going to be a thermal spectrum associated with it. Yeah.
Is it only kernel for negative frequencies or also for positive frequencies? Because you are...
Oh, okay. Now, the formula which you have written down here, if I flip the sign of nu, whatever you get with this minus beta nu is true for other frequencies as well. Okay, so I don't know what exactly you mean by whether it is thermal for only positive frequencies. Suppose I say that I have a power spectrum P of omega, which is proportional to 1 upon e to the beta omega minus 1. This is what one would have normally called a thermal spectrum. Now, if omega is greater than 0, then this is a honest to God frequency. But when omega is less than 0, I can still write down this formula and I will get something else. Right? So, that is the correct extension of the Planckian spectrum for omega which is less than 0. So in that sense, it doesn't make any difference. Okay. So what is essential is that suppose you take P of omega and P of minus omega. Since it came up, let me explain that. This is 1 upon e to the minus beta omega minus 1, which I can write as e to the beta omega upon 1 minus e to the beta omega. Correct? I haven't worked anywhere in algebra. So if I take, let us take P of omega divided by P of minus omega. Then the denominators cancel out except for minus signs. And then in the numerators you get e to the minus beta. This is the real characterization of a thermal spectrum. The power in the thermal spectrum for positive frequency and negative frequency are related by the Boltzmann factor. In the quantum field theoretic context, the positive frequency modes are going to induce transitions in one direction, negative frequency modes are going to induce transitions in the other direction. If their amplitude are related by this factor, then if the populations are related in the inverse direction, it will come into equilibrium. Okay? So this is the only feature I need. And whether I start with P of omega or P of minus omega depends on the context. Fine. So we have this result, and as I told you, it is coming out of just this exponential redshift. And many of you probably will know that if I have a real black hole, like a short-scale black hole, and there is radiation which is being emitted, again real radiation, an observer who is falling into the black hole is emitting pulses of radiation which is being received by an observer far away. And you ask how the observer who is far away is viewing this radiation. How does the frequency of the radiation appear to the observer who is far away? Assume that the guy who is emitting the radiation is emitting a monochromatic radiation as far as he is concerned at the same frequency. But as he goes closer and closer to the horizon, it is going to be redshifted more and more, and it will be exponentially redshifted. So an observer who is at a large distance will be detecting an exponentially redshifted spectrum. And that exponential redshifted spectrum, if he Fourier transform, he will say that it has a thermal spectrum, and he will get exactly the same result with the correct factor. The only question is, there are no observers around a black hole who is emitting laser light at you. And that is provided by the quantum field and the 0-point fluctuations of the quantum field. The mathematics of the analysis is identical to what I did here. The physics requires an input of a wave, and that wave comes from something else in this field. Okay? So that is basically all that I wanted to do as far as the classical part of this is concerned. And now I want to move over to quantum field theory and some aspects of quantum mechanics. So I believe we started again at 4:30, right? So if I go on till say 5:30, that should be all right? Yeah, so I'll stop at 5:30. Okay, so I'll plan things. Okay, so now let us go back and start thinking about the quantum theory here. So here again, just as I started with Lorentz transformations, even though it is an advanced course, I want to start at a very basic aspect about quantum mechanics and quantum field theory, because again I find that it is inadequately discussed in textbooks. In quantum mechanics, one of the nicest ways about thinking about particles going from point to point would be something like this. Let me take x, let me take t, and take one point here and another point. And let us take any path which connects these two. Then you say that in quantum mechanics the particles can go via any of the paths, like this. And you attribute a particular amplitude which happens to be e to the I times the action for that particular path to any one of them. And then you sum over all these paths to go from 1 to 2, and that will give you the path integral kernel. You go to 2 starting from 1. Then if you multiply it by the amplitude for it to be at some point 1 by a wave function, and you integrate over that coordinates, you will get a wave function at the other end. Okay? This is the standard path integral formulation of quantum mechanics. Now let us stare at these paths a little closely. In order to do that, let us also look at the same paths in the xy plane. Suppose think of a particle which is moving in x, y, z, t. So I want to draw similar kind of paths in the xy plane. The x remains the same. Here now it is not time, but it is the y-axis. Okay? And the point 1 has some coordinates here, point 2 has some coordinates here, in the x and y. Now I want to think of particles moving in the xy plane. Now I can think of paths like this, paths like this, etc. Okay? Now there is a basic difference between paths I drew there and paths I drew here. Here, a particular path can cut, this particular path can cut the parallel to this y line in 3 places. That's okay, the path can just wind around. The particle is going to that point from this point over some time, and it goes like this. Okay? So it could have been at a given point in the x-axis 3 times in that path. Who cares? But here, if I draw a line like this, I am not allowed to draw paths which, for example, would have done something like this. I am not allowed to do that. In non-relativistic quantum mechanics, when you evaluate the path integral, either by time slicing or by introducing a whole lot of brass and cats and integrating over, you make sure that at any given time t, the path hits it only once. In fact, if you go back to your basic Feynman and Gibbs, when you evaluate the path integral, you are going to take one time slice and you integrate over the value of the path, the value of the x coordinate the path is going to take from minus mu plus infinity, then go to the next time slice, etc. So at each time slice, the path cuts only once. Again, no big deal. You accept it on faith and say, oh, that sounds good. I mean, after all, we don't want a particle to be found in 3 different places at the same time. Okay? So we had only one particle, so it looks sense. Now you go to relativistic field theory. Not even field theory, relativistic quantum mechanics. So I want to bring in relativity. In relativity, I do have particles and I do have paths. So I should be able to write down a path integral like this. Except that in relativity, somebody tells me that I have to treat time and space at the same footing. So what I can do now is that I can take the proper time tau and take the space coordinate, and I can go from 1 to 2, and I can draw paths like this. These paths should cut these only once. I am not allowed to do paths like this. This is forbidden. So here I am plotting the proper time as carried by the particle. So when the particle is moving, at any given proper time, it is at one point, at some point. I don't know where, but it is only at one point. It is not at several points. So in proper time, it can do only this. But what about coordinate time? The coordinate time t in relativity is just like y-axis. So in the xy plane, I could do this, which means that in coordinate time, in relativity, if I do t and x, and I go from point 1 to point 2, I am perfectly legitimate in talking about paths like this, or paths like this. Okay? Because these are just like these paths. I was allowed to do it here, I am allowed to do it here. Particles go forward in proper time, but they can go forward or backward in coordinate time. Just as particles go forward in absolute Newtonian time, but they can go forward or backward in the y coordinates. So there is a complete parallel. So far so good, and in fact you can do quite a bit of quantum field theory using this proper time. It is known as the Schumer's formulation, and it is the basis of source theory and all that. You can do that. But we don't like to do that. We don't want to introduce the proper time of the particle in order to do quantum field theory or relativistic quantum mechanics. So we want to stick with this. If we want to stick with it, then we want causal propagation of the system from one time to another. So I start with this time. The particle is either here or here in 2 paths. Then I go to this time. I'm in a bit of a trouble because the particle is at 3 different points at the same time. Okay? So I want to, then you can immediately see what is happening. I can go here and the particle is at 10 different points at the same time. So in particular sense, if I think an equal infinite number of times, the particle can be at an infinite number of points at a given time. So if I want to describe the system by evolution from one time to another, which is what I like, as I said, it is just my personal taste. I would have done with this without that. But if I like this, then I need something which is capable of encoding the degrees of freedom at a constant time slice, which this picture represents. This picture tells me that there are 3 particles, therefore I need 3 degrees of freedom. I mean, suppose, assume for a minute that each particle is described by 1 degree. It could be described by 6 degrees of freedom, 12 degrees, I don't care. If whatever is required for 1 particle, I need 3 times that. By the time I get here, I need 10 times that. And since there are paths which wiggles infinite number of times, I need a system which has infinite number of degrees of freedom to describe this relativistic propagation of particles from one point to another. If I insist I want to go on this time slicing, such systems are called fields. Okay? So the reason we introduce fields is just because of this. It is nothing deeper than that. So because fields are a very convenient way of describing infinite dimensional systems. Yeah.
May I ask a question? But isn't that only the case if you want to allow for superluminal motions?
Here.
Yes.
No, it is.
Otherwise,
so
if it goes forward in proper
the
time,
moment
it
if
also
it has to
goes
go-
forward also in coordinate
That's
time.
right. If it has to wiggle and come back.
So here your path goes backward in coordinates time.
Yeah.
So this means
Superluminal.
Yes, that's what I'm
That's
saying.
what I was saying. That
Okay.
if-
You allow for superluminal motion.
If I want
Only
to
then
go
you
back
have
and
this.
forth,
Yeah,
it has to cut across the light cone.
exactly.
Right? I have drawn a 45-degree line. But now think of the following situation. This is T, this is X. Let me start from the origin. And let me draw the 45-degree line. And consider the following path. Okay? From the origin to this point, it is not superluminal. But inside, if I go and take this point and draw the light cone, it is superluminal. So it is superluminal in a slightly subtler way. Maybe that is what you meant. It should not be superluminal anywhere.
Yeah, it's locally superluminal.
Locally superluminal should not happen, but not with respect to the initial point and the final point. So sometimes people think that the reason we need quantum field theory is because there is a propagation outside the light cone. That is, if I take the initial point 1 and the final point 2 outside the light cone, classically I don't expect a particle to go from one to another, but quantum mechanically there is a small decaying amplitude for it to be found there, and therefore I need quantum field theory. What I am saying is that is not the true complete picture. Even when the initial and final points are well within the light cone, you need that picture because the paths are wiggling superluminal. So in that sense it is correct. Okay? Fine. So now we need a system which has infinite degrees of freedom because the same particle can be found at infinite number of spatial points at a given time t because of such paths exist when you do the sum in relativity. So you just combine path integral formulation with an action for a relativistic particle and you use the fact that time is like space in relativity and only proper time is something which goes forward and you end up with them. Okay, so now let us ask how I am going to describe them. What do I want to do at any given time t? So let us try to approach quantum field theory in a very naive, constructive way rather than starting from a field and quantizing it. At any given time t, I want to describe the state by saying that there are a certain number of particles because the number of particles we have said can change. So I will start by saying that a state in general for me is given by a set of integers, let us say. This is my state. Just to be more convenient, I will denote it as n with a vector k. So this is, I am just using the momentum to label the particle. So take each particle, let us say it has a particle momentum h cross k, and nk tells you the number of particles which I have with a vector k. Now I will not nitpick over the continuity and things like that because very technically n of k d3k over 2 pi the whole cube will give you the number of particles between some point etc. It may not be an integer value distribution, so I will take cumulants and take derivatives. But none of these complications affect anything, so we will work naively and I will assume that k is discretized if needed in a large box and then we will take the continuum limit. Yeah.
So I didn't understand. At some point are you assuming that there is a frame in which causality is preserved or not?
Causality. Maybe I am, but I didn't need it anywhere. So why did you bring that up?
Well, yeah, the point is that when you go to this last one, right?
Yes.
You were assuming that there is a frame in which the right diagram holds or not?
This right diagram.
Yeah.
No, this right diagram always holds because this is with proper time and x.
Okay, so you assume that there is a frame in which...
No, it is a frame independent statement. You see, if I take xi of tau as a path, where tau is the proper time, and I do a path integral in proper time slicing, which is known as the Schwinger's proper time method, then everything works, and I can write down the standard kernel as an integral over the other one. So that is perfect, because that only, and there I can have any kinds of paths going back and forth. Except that the path should not go back and forth in the proper time, just as you didn't want it to do that here. Okay. Yeah. Alright, so you have a state which is described by this. So I want to have a system in which this can be used. This state in particular should have an energy which is given by the number of particles Nk, h cross k, or h cross omega k, if omega k is the energy corresponding to this, and summed over all k. Okay? Yeah.
Sorry, what motivation will I have to go to any coordinates if it seems that there is a privileged coordinate which are in the proper time? In the proper time I have a quantum, it's like very different from other coordinates. Why will I need to formulate my theory in any...
Okay, the proper time is not a coordinate. The proper time is something, see, okay, first of all this picture right now is in inertial frames. Okay, I'm not even going to go into Rundler frame because I want to first describe everything in inertial frame and then introduce the complication. So the t and x are standard Cartesian inertial Lorentzian coordinates. The proper time is not a coordinate, it is just a parameterization. What I am saying is that think of curves xi of t, tau, such that when I change tau continuously in forward direction, the curves only have a unique value for every value of tau. They don't look back. Let us go back here. Here, why is it that I excluded this path and I kept this path? Let us first try to understand that. This is non-relativistic quantum mechanics. Okay? Now, the reason I did that was the way I defined my path integral, I have to do the time slicing and do the integrals over that. That is the only way I can give meaning to this mathematical expression. So, if I want to do that in relativity, just as I would have done here, if I do one-dimensional path integral, I will have just x as a function of t, two-dimension x and y as a function of t, three-dimension x, y, z as a function of t, four-dimension x of tau, y of tau, z of tau, and t of tau. That is how I have done here. So I am just thinking of t as just like a coordinate, and I am using a time which is the proper time. Okay, so it is not a preferred quantity or a coordinate because I am not using any preferred coordinate. The full relativistic invariance, full Lorentz invariance, special relativistic invariance will be maintained in this Schwinger's formalism. That is not an issue.
And this tau is different for each path.
Exactly, it is different for each path. I mean, it is just parameterizing the path. Okay, so yeah, but anyway, nobody except Schwinger and probably me in my weak moments like this approach. I mean, it's calculationally very convenient, but that is not the way quantum field theory is done. Quantum field theory is always done in this way. But that is what I am going to introduce. So here, I need something which will have infinite number of degrees of freedom. So the infinite number of degrees of freedom is quantified in terms of the number of particles in different states, and the energy should linearly add with this and k. Right? So what physical system can I use? What is the simplest physical system where the energies are quantized in integer values? I mean, the harmonic oscillators are a very natural choice. So I'll start with the Hamiltonian for one harmonic oscillator, which is half pk square plus omega k square qk square. Right? And the corresponding Lagrangian would have been half qk dot square minus omega k square qk square. Where omega k square at the moment is an arbitrary function of k. This is some derivative. Then I am going to say that I have a whole lot of oscillators, so I have to sum over all the k. Okay. Better still, when I am looking at the continuum limit, I will think of it as integral d3k over 2 pi the whole cube half cube k dot square minus omega k square q k square. Fine. Now something remarkable happens. It turns out that the same Lagrangian can be obtained if I start with a Lagrangian. Let me write this as minus half because of my signature di of phi where phi is a scalar field, and I Fourier transform this phi of t comma x. I write it as integral d3k over 2 pi the whole cube qk with a capital Q of t e to the I k dot x. Ideally, I should work with action here itself. So let me write this as action as summation over k integral over dt. So this will also be another integral, and there is a dt here. Okay, that is somewhat easier to think in terms of. So here also let me write down this in terms of the action. So this is integral d4x, Cartesian coordinates. So let us pass and understand what it is. So here I write down a classical action for a scalar field phi, which is a function of t and x. Di stands for the usual time and x, y, z. And this minus sign is because I am using minus plus signature. So this is just the kinetic energy term for an action, which means it is a simple massless scalar field. Now I take this action and I just Fourier transform this phi of t comma x in terms of some Fourier modes qk of t, just in spatial Fourier transform, and I plug it into this. So you will have a phi dot square term, which will just give me, if I put a dot here, I'll just have a dot here, and then when I take the square of that, I'll just get modulus of qk dot square. The reason I kept this as capital while this is lowercase is because of the small complication that this qk of t is not real. Because phi is real, you have the condition that q of minus k should be equal to qk star. Of course, that is not a big deal because it just says that for every k, the diametrically opposite k is related to it. So if I separate this qk into some ak plus ibk, then a of minus k is same as a of k, and b of minus k is minus b of k. So I can just double the modes by taking real and imaginary parts and taking away half of the k space. So once I do that, I can map this qk to this. These qk's I want to be real. So that is why I just kept a distinction between these two. If you just forget that distinction, nothing will go wrong. Okay, you can just put a modular sign on that. So you take this Fourier transform and you plug it in. When you plug it into this, the phi dot gives you this qk dot square term. Then I have a del phi square term. That del phi will produce a ik here, and then when I take the mod square, I will get k square times qk square. That means this is going to be equivalent to this with the condition omega k square is equal to k square. I could have easily added another m square phi square term, one more quadratic term. Then this omega k square relationship would have become this plus m square, and the action here would have picked up is the only place where the relativity comes in. So this is actually quite remarkable. So we have to spend a little bit of time to understand that. This particular line of attack to the right of this knows nothing about special relativity. I said give me a quantum state labeled by integers. If you are doing solid state physics and you are treating magnons as particles, then I would have said magnons have a particular dispersion relation in my ferrite crystal, and that is given by omega of k. The energy depends on the number of magnons times h cross omega k, and I would have done the field theory in that context exactly like this. I would have treated magnons as particles, they will scatter off each other, they will exchange energy and momentum. I will write down an action. None of this will have anything to do with special relativity. Here, the only place where special relativity comes in is this Pythagorean relation. The omega k square, if it is k square plus m square, then by multiplying everything by h cross, and there is a h cross already implicit in this, yeah? Once you multiply by this h cross, you can think of energy and momentum being given by the relativistic dispersion. Therefore, your relativistically invariant action, which is here, special relativistically invariant action, naturally leads to the same thing. Okay. So this is all basically quantum field theory is all about. You start with a field, you decompose into a whole lot of harmonic oscillators coming via this route, and then you have an action which describes the sum of the harmonic oscillators. The states of the field are described by the integers, because each oscillator has a particular quantum state which is given by an integer, and the collection of all oscillators is given by the collection of all the integers. So you give me this. You know what state of the field I am talking about. And that is all there is. And then interactions will allow this number to change. So the nk goes to nk plus 1 or nk goes to nk minus 1, and you have to add an interaction term which will take care of that. Okay? So I don't know how many of you have done quantum field theory before, but this is just a rapid orientation as to how quantum field theory and their states come. The state we are particularly interested in is a state called vacuum state, but maybe that has to wait for the next lecture, because if I start there, I'll have to break halfway through. I'll stop here. So, is there any questions on this, both the parts? Okay, good. So we'll meet on next Thursday.